We are covering capacitors and inductors in the first parts as a quick reminder, since we'll be benefiting from them in the first order circuits. So the capacitor can be a parallel plate capacitor. It's used to store energy. The current flows. This is the characteristic equation of the capacitor. And as I mentioned, charge stores on the cap, and you should definitely know this characteristic equation. This is a definition for a parallel plate capacitor. This is the distance between the plates. This is the area, the section of the parallel plate. This is the epsilon, the permittivity, and there might be sometimes a structure between. The Q is the charge. And so in this equation, this one is the cap, right? Q over C. So the 1 over of that is the charge. Important to remember in this slide is the voltage across a capacitor never change instantaneously. Why do we say that? Because we are actually taking the derivative of the voltage, and that's the current. So basically, if the voltage change instantaneously, then that means currents go to infinity, and that doesn't really happen in an actual circuit. This is an example for yourself. You can solve it. If there is, for instance, a voltage function. From this voltage function, it's asking you, we have a cap, and that's the voltage on the cap. So what would be the current, right? So we take the derivative of the voltage. This is the slope at this part, and this is the slope at that part, right? So that's simply the capacitance equation, the characteristic equation. That might be the vice versa. I might give you a current, and then I can tell you, hey, the initial voltage on the cap is 0. So that's what would be the voltage characteristic. Then this is the equation for the cap, right? You take the integral of the current divided by C. So that's how much voltage is accumulating in the cap. But of course, there's the initial voltage. We have to sum that up, right? Basically, it's this part, V0. And then it sums up. So basically, we're taking integral of the current, adding it to the 0, right? Then it becomes this function. The integral of a linear curve is a parabolic curve. X becomes x squared over 2. Then we take the integral of this, which is basically the integral of a square. And 0 to 1 is this part. 1 to 2 is this part, more linear, right? Since it's a square. And after 2, so it becomes constant. So more examples I won't be solving. That I uploaded the slides. Why are we using capacitance? The capacitance have different purposes. For instance, a constant DC current cannot flow through a cap. So that means a constant voltage also cannot change. What does it mean? So when we have a cap connected to two sides, this is, let's say, Vx, and let's say this is Vy. At DC, which means frequency of 0, yes, it is open, right? Because the cap is 1 over j omega c. In the Laplace, omega is 0, so this goes to infinity, right? So that means at frequency of 0, this cap acts like an infinite impedance. Infinite impedance means it's open. So if any voltage at this side at frequency of 0, we don't see it here. So why do we use this? What might be the benefit of that? The benefit of that would be if we have two amplifiers, the DC voltage of this point, sometimes cannot really run the circuits. Sometimes they are not compatible. So we just use a large cap between these two amplifiers so that DC-wise, they are disconnected. That's called coupling. So they are not coupled so that we can bias this part with some biasing circuits. We put a voltage here and stuff. And so that we can run this amplifier, second amplifier, with a different voltage. Sometimes the DCs are just compatible and we don't really use this cap. We just basically short them so that they are coupled. Okay. So whatever signal here becomes the input signal. All right. And an alternating current can flow through cap. What does it mean? Well, alternating current means any frequency other than 0, right? The 0 frequency is DC. Any frequency other than 0 is AC, right? That you can represent with sinusoids, because any signal can be represented sum of sinusoids, like you learned Fourier series probably. So that's why we use sinusoids. And when we apply a signal here because this is not infinite anymore, right? Because omega is not 0. Then this cap has some kind of, let's just put resistance, but it's not resistance, it's impedance. This has a complex impedance. So that the signal goes from here to here. Okay? So it's not open anymore. The mechanical analogy is here. It's just saying that, for instance, air cannot pass through a window. But alternating pressure can make the window vibrate. So you can think air just like voltage, and you can think the alternating pressure just like the AC signal, for instance. What happens when they are parallel? What happens when they are series? So if they are parallel, opposite of resistances. So you just sum them up, C1 plus C2. But if they're in series, you treat them like parallel resistors, right? So now C1, C2 in series means the just like parallel resistance becomes 1 over C equivalent becomes 1 over C1 plus 1 over C2. And the reason is coming from the concept of charge. For instance, in the case of the two caps, well, let's check C. So here, the total charge, this one is Q, and what should be the charge in this one?
Q.
It should be Q, right? Because they have the same current. Q is current times time. So since they're in series, their current is same, so they should have the same Q. So, that's where the proof is coming. Yeah? So you can check these slides. I won't really have time to explain the proofs, but these are certain things that concepts you need to know. This is how a capacitance charge, for instance, when we have a cap, and then the cap will have some current on it, and let's say cap has an initial voltage of 0. Then that means we start from 0. Cap has an initial voltage of 5 volt, then we would start from 5 volt, right? So that's basically showing the base it starts. Then when the current flows, this cap starts to accumulate more charge and eventually charges, and eventually comes to a point. And these charges, for simplicity, we define something called time constant. And this time constant here is in the equation, minus T over time constant. So this explains time constant here again. The important thing is, don't forget that we are still doing nodal equation. So actually when we have the circuit connected, right, through the switch, what happens is IR is the voltage drop here, V is the voltage drop on the cap, and then we come back to the VS, it is the voltage of the source. And what we do is we write the current in terms of the cap and voltage right here, right? And then we replace it here, and then you have the first order equation. And the first order equation, you just make sure that the derivative coefficient is 1, but we divide all sides to RC, okay? So this goes away, this becomes RC, and this becomes RC. Then this is a first order equation, first order differential equation with constant coefficients, and you should know how to solve this first order equation. So when you look at it, to understand how the circuit works, just put T equals 0 here, and when T equals 0, what is this term? Exponential term. T equals 0 olursa bu term 1 olur. Exponential 0. 1 eksi 1 0 olur. Ama dolayısıyla VT 0 olur. Dolayısıyla time 0'da gördüğünüz gibi VT 0. T 0 değil de infinity olursa ne olur? Exponential minus infinity. Exponential minus infinity 0 oluyor. 1 minus 0 is 1. Vs times 1 is Vs, right? So that it comes to the Vs. So eventually at a certain time, which this T is actually 5 time constants, it's 99% of the cap has charge, right? So then eventually at T equals infinity, the cap charged fully, but 5 time constant is actually enough to charge 99% of it. All right, so that is how the cap charges. Similarly, that's how it discharges. What does it mean? Well, the charging equation was 1 minus exponential. Well, discharging equation, there won't be any 1 minus. This time it will be just an exponential, right? So this is decaying exponential. Exponential minus, okay? If we make it 1 minus, then that would be charging, right? Exponential means decaying. So this is the discharge equation. Well, the discharge equation, let's connect switch here. Now the circuit becomes this. And here that means there is no Vs anymore, right? So it's actually the nodal equations becomes this one. And same logic, you write the currents and voltage characteristic of this cap, I equals C dV dt. You put it here, and the equation becomes this. This equation doesn't have any fixed term. It only has the exponential term, right? In the previous one, it had another term. Remember? It had two terms which are Vs and Vs times exponential. We are subtracting them, and that's because of this forcing function. So there is a one homogeneous solution of a differential equation. The homogeneous equation is basically an exponential, and then there is a forcing solution due to this forcing function. And this forcing function is whatever it is, it tries to mimic. So the natural equation, natural solution is exponential, and and the forcing solution is mimicking the forcing function, and it becomes Vs. Okay, so quickly you can make a check. Well, what if I put Vs instead of the V? What is the derivative of Vs with respect to time? Vs is a fixed voltage. Question is, we have this Vs voltage, so I'm just quickly trying to find the solution of this first order differential equation. So the first order differential equation is here. Our variable is voltage on the cap, and we found the nodal equation, we put the characteristic equation, so we have this equation. So quickly trying to find the forcing function solution. So question is, the solution wants to mimic always the forcing function, so it should be a function of Vs. So I was saying that what is dV over dt if V is Vs? If I put V equal Vs, a constant here, what would be the derivative of a constant? 0, right? So when I put V equal Vs, well, this goes to 0. The entire thing goes to 0. Well, this V was Vs, so the equation is satisfied, okay? As you can see. So that's where that Vs is coming from. Okay, that's the first solution. Then the second solution, so say the derivative of 5 volts is 0, right? Derivative of a constant is 0. Dolayısıyla bu 0 oldu. Burası zaten Vs'ti. Vs equal Vs. Kanıtlamış olduk yani. Bunu birazdan daha iyi bir şekilde anlatacağım ama bir first order differential equation'ın 2 tane solution olduğunu bilmeniz lazım. 2 solution derken 2 tane term var. Birinci term, ikinci term. Bunu şu şekilde yazabiliriz değil mi? Vs eksi Vs exponential TRC. So ilk solution'ı forcing function solution'ı. İkinci solution'ı da homogeneous solution. Yani biz şunu 0 yapıyoruz. Ve bunu 0 yaptığımız zamanki solution'ı buluyoruz. O bu. Bir de forcing function. O zaman forcing function'ı gene tekrar yerine koyuyoruz. Forcing function olduğu zamanki solution'ı buluyoruz. İkisinin superposition olmuş oluyor. Gördüğünüz gibi deminki bu charging circuit, çünkü burada Vs var. Discharging olduğunda Vs olmayacak. Yani sadece bunu 0 yapıp natural solution'ı bulmamız yeterli olacak. Çünkü orada Vs yok. Dolayısıyla bunun sadece bir solution'ı var. O da bu. Ama buraya charging circuit deseydim ve devre bu deseydim, o zaman burada bir forcing function olacaktı. Let's talk about inductors quite a little bit. Inductors are fantastic. They actually do a lot of things. This is a huge coil, transformer, and inductor, right? So flux, as you see, this is the equation for the inductor. There's a L coil, current flows through it, and a voltage is on the coil. The değişen akım voltaja ne? This is Faraday's law. Okay? And here this one is flux. The flux is changing on the coil, and because the flux is changing, we multiply this flux change with the number of coil turns. N is the turn. Kaç kere döndüğü. Bu size voltage yaratıyor. Dolayısıyla şuradaki flux'ı L çarpı I diye yazabilirsiniz. Yani şu flux yerine Li yazdığınız zaman N2B yerine buradan buna geçmiş oluyorsunuz. Bu da sizin zaten inductor'ınızın karakteristik equation oluyor. The charging discharging mechanism. So just like the RC circuits, the inductance also charges and discharges. When the current is constant, L di over dt is 0, right? No voltage. And when the current decreases, well, this means the derivative is minus. Therefore, voltage over the coil is smaller than 0, okay? Just like the cap, you have the same logic, but the logic is voltage and current is flipped, like vice versa. We have a voltage source here, and this voltage source, sometimes they use this, sometimes this. This voltage, we have a RL. If I ask you, hey, what is the current on this inductor initially? As you can see in this equation, if you put T equals 0, this becomes 1. 1 minus 1 is 0. So the current is 0, right? What when it is charged? When t is infinity? V over R. Similar to cap, as I mentioned. So instead of the voltage, this time it is current that is charging. So initially your current is 0. No current here. But then slowly the inductor starts to charge, which means now it is storing current through this inductor. Current is increasing, and it comes to a final value. So this final value is V over R. Voltage on this inductor becomes 0. Why this becomes 0? Because this inductor now has no change of current. Right? So what is the equation? L di over dt equals VL. Eğer indüktör üzerindeki akım değişmiyorsa derivatifi ne olur? 0 olur. Değil mi? Değişmeyen bir şeyin derivatifi 0. Dolayısıyla bu ne olur? O da 0 olur. Yani neyi gösteriyor? Artık şurada akım değişmediği yerde voltaj artık 0. Okay? Cap'te olay neydi? Cap'te tam tersiydi. C dV dt eşittir I'dı değil mi? Şimdi cap'i hatırlayalım. Voltaj artık cap'te şöyle charge oldu voltaj. Şu noktada voltaj değişmiyor. Akım geçmiyor artık değil mi? Dolayısıyla şurayı çizersem RC'de, şurayı da voltaj source çizelim. Charge oldu. Cap charge. So cap charge, this doesn't change anymore. Current 0. Dolayısıyla cap artık open circuit gibi davranacak. Niye? Çünkü artık üzerinden bir akım geçmiyor. Fully charged. Dolayısıyla T infinity'de artık akım geçmeyecek. Değil mi? Çünkü şurası 0. Inductor'da da similar logic. Akım geçti ve akım sabit. Şuradayız mesela. Değil mi? Akım sabit. Akım sabitse artık voltaj 0. Yani o zaman kapasitansın tam tersi. T infinity'de ne oluyor inductor? Kapasitans open. Değil mi? Bunu anladınız. T infinity'de. Çünkü artık şarj olamıyor. Voltage wise. Değil mi? This doesn't go anymore. It charged already. Biriktirdi. Şuradaki voltajla aynı seviyeye geldi. Artık akım geçemiyor. Dolayısıyla cap is open at T infinity. Inductor T infinity'de ne olur?
Short circuit.
Short olur değil mi? Çünkü voltaj 0. Üzerindeki voltaj 0 demek ne demek? Short circuit'te. Dolayısıyla akım birikti ve en sonunda akım sabit olduğu zaman artık bu short circuit olmuş oluyor. Okay? First order devrelerde bu zaten. Yani RC ve RL characteristic equation'lar. Okay? These are the characteristic equations of RC and RL. One difference, RC circuit'ta şurası exponential eksi t bölü rc'ydi. Burada exponential t çarpı r bölü l. Bu da aslında zaten nodal analiz yaptığınız zaman, yani şunu çözdüğünüz zaman ki solution'dan geliyor. Neden öyle dersiniz? Okay, well, so LC devrelere girmiyorum. LC devreler second order oluyor çünkü. First order olması için ya bir cap ya da bir inductor olması lazım. If bir L ve C de varsa o zaman second order. Second order ne demek? Equation'da artık şu aşağıda ikinci derivatifi alıyorsunuz demek. Bu inductor'ın karakteristik equation'ı, kapasitörün karakteristik equation'ı. Şurada da demin dediğimi anlatıyor. Buna bir mesela kapasitansa constant voltage uyguladığınız zaman ne olacak? O constant voltajı pat diye mimikleyecek. Dolayısıyla hemen hızlı bir şekilde charge olacak. Niye? Çünkü R 0. R sizin ne kadar büyütürseniz charge olması o kadar yavaşlar değil mi? Eksi T bölü RC. R'ın 0 olduğu bir devrede time constant'ınız da 0'dır. Pat diye hemen charge olacak. Dolayısıyla belli bir hemen charge olduktan sonra ne oluyor? Open circuit oluyor. Çünkü bu voltaj o voltajı mimikliyor. Dolayısıyla arada bir current geçişi olmuyor. Inductor'da da current için geçerli bu. Eğer bu inductor'a bir current source'a yaparsanız şu şekilde üzerinden bir akım geçerse bu akım hemen bu inductor'ı şarj ediyor pat diye. Değil mi? Şu charging olayı siz hemen böyle çok speedy görüyorsunuz. Çünkü arada bir rezistans yok. Dolayısıyla artık akım değişmiyor. Akım fix. Dolayısıyla buradaki de short circuit olmuş oluyor. Okay.